Hi everybody. Today we are going to talk about how to find the area under a curve, which you guys will see is one of the most fundamental skills that you will be learning in calculus. Alright, so we're going to start by approximating the area under a curve using rectangles. So you're going to see that the fundamental skills and the fundamental concepts that we learn using this process, you'll be using them in more complex concepts. So it's really important that you understand what's going on with the more basics before we move on to the trickier stuff. So they would like us to find the area of the region bounded by this curve f of x, the x-axis, and the two vertical lines x equals 0 and x equals 10. So we have a parabola, looks something like this. Sorry, that's a horrible parabola. Let me try that again. We know that the vertex is at 0, 2, and it's upward facing. So here's the vertical line x equals 0. Let's just call this x equals 10. And they want us to find the area of this region. So like I said, we can't look at this and there's no formula that we know of to help us find the area of a shape like this. So we're going to see if we can take this area and to split it up into shapes that we know, such as rectangles. And we know how to find the area of a rectangle. So let's say I take this and I split it up into 5 evenly spaced rectangles. And those rectangles are going to look like this. So once again, the reason why it's useful for us to do this is because we know how to find the area of a rectangle. While this curve is not a shape, we know rectangles are. So one thing you'll notice right off the bat, that if I find all of these areas and add them up, this is going to be an overestimation. So you can see all of these clear parts, it's part that is not under the curve but will be counted in our area, which is why this is an approximation. So let's start by reminding us how do we find the area of a rectangle. So the area of a rectangle is going to be the base times the height. So we can find this base, or I'll call it the width of each rectangle, by taking this entire interval, which would be 10 minus 0, and splitting it up into 5 equal parts because there are 5 rectangles. Sorry, 5. So I can see that the width of each rectangle is going to be 2. Now I can find the height of each rectangle by evaluating my function f of x at each x value here. So I'm going to evaluate my function at 2, 4, 6, 8, and 10 because I see that is the height of each of these triangles. So height is just going to be f of x for these 5 x values. So we are going to need to know what is f of 2, f of 4, f of 6, f of 8, and f of 10. So we're going to evaluate those in our function. So we get 6, 18, 38, 66, and 102. So now that I have the width and height of each rectangle, I can find the total area by finding the individual areas and adding them up. So the area, or approximation for the area under the curve, is going to be width times height of that first one, width times height of the second one, so on and so forth. And of course, since they're all being multiplied by that same width, we could have just done 2 times the sum of all these just to save us time. But if you plug this in or you calculate this, we should get an area of 460 units squared. So remember, we did point out that this is an overestimation because of these clear parts that are part of the rectangles but are not part of the curve. But, it's kind of somewhat close to what that area under the curve looks like. But I'm wondering if there is a way that we can make this more accurate. So I'm wondering what would happen if we doubled the number of rectangles. What if instead of 5 rectangles we had 10? So now let's go in and add these rectangles in here. And let's see if that actually saves us any space. So here it kind of goes like this now. So you can actually see that we are going to be eliminating some of that part that is the overestimation. This is gone, this is gone, this is gone, this is gone, and a little bit is gone here. So I can see that just by drawing my rectangles before I even calculate the sum of those areas, I can see that I have less of an overestimation. So let's confirm that with an actual calculation. Now, obviously, the width of each of our rectangles is changed. So we still have the same total interval, but now I need to split it up into 10 parts. So the width of each rectangle here is going to be 1. And then to find the heights, I'm still going to evaluate each of these x values at f of x. We already have half the values. Now we just have to do f of 1, f of 3, f of 5, f of 7, and f of 9. So like I said, we can still use these same values to help us calculate these areas. So f of 1 is going to be 3, f of 3 is 11, and then we have 27, 51, and 83. So now for this area, the width of all of my rectangles is 1, and then I take the sum of all of these values. So 3 plus 6 plus 11, all the way up to 102. So if you find this area, we actually get an area of 405 units squared. So while we know that this is still an overestimation because we still have this part up top that's not really under the curve, if you compare those two, just by doubling the number of rectangles that we already have a much better approximation. So the main idea that I want you guys to take from this is that the more rectangles you have when you're approximating the area under curve in this way, the more accurate your approximation will be. All right, go ahead and pause the video and see if you can give this one a try. Find that area using first 4 rectangles and then try it with 8 rectangles. I also would like you to do this completely without a calculator. Yes, there are fractions, but make sure you can work through that by hand. Okay, so let's check our work here. So you can see that when we have 4 rectangles, the width of each rectangle is 1/2. 2 minus 0 is that total distance, and I split it up evenly within 4 rectangles. And then I'm going to evaluate my function at these 4 values to find the height of my rectangles, and then base times height plus base times height. Add them all up, and you should get 9/2 units squared. For 8 rectangles, you'll see that the width of each rectangle is going to be 1/4. So you have to evaluate a few more functions, and then you have 1/4 times the sum of all of those, and here you get 17/4. So here, this is 4.5 units squared, and this is 4.25 units squared. So you can see that by doubling the number of rectangles, we have a more accurate answer. All right, so now let's see if we can find a way to have an even more accurate description of the area using summations. And we're going to base that off of this concept that we generalized, that more rectangles leads to more accuracy. So that's going to be a really important concept for us to understand. Okay, so let's start by, I'm going to zoom way in here. Let's draw a curve. Let's call this curve f of x. And let's say I'd like you to find the area under this curve between the intervals a and b. So I'd like you to find the area under this curve. So let's say we start drawing in a couple rectangles, like here and here and here. And we're keeping in mind that the more rectangles we use, the more accurate our approximation will be. So let's start by defining the width of each rectangle. Well, as we did with the other problems, the way you calculate the width is you find this distance. So we can say that that's b minus a. and then we divided it by how many rectangles we have. So I'm going to call n the number of rectangles. So you might guess that since we're using limits, we're probably going to want to find some way to find a limit where n is approaching infinity. Because once again, the more rectangles we have, the more accurate our approximation will be. So we found a way to assess the width of each of these rectangles, but now I need to find a way to find the height of each of these rectangles. And I know that's going to involve us evaluating the function at these x values. But maybe you're wondering, well, how do I define this x value? There's no numbers here. So let's see if we can find a way to describe this x value. I know that this distance is a, and I know that this is the width of our rectangle, which we've defined as b minus a over n. So I can describe this x value as a plus b minus a over n. Okay, let's see if we can find a way to describe this x value. Well, that x value is just a plus a width plus a width. So we can describe that as a plus 2 times b minus a over n, 2 of our widths. And then maybe you're catching on, this can be described as a plus 3 times b minus a over n. So you might be noticing that for each new term, the only thing that's changing here is the number of widths we need to add to find our x value. So the next one would be a plus 4 times our width, a plus 5 times our width. So if we were doing a summation, this value right here would be our I value. So let's see if we can write this as a height. So we need to evaluate this function f of x at these x values. So it's going to be f of a plus I times b minus a over n. So remember, this b minus a over n is just the height. Oops. It's just the height or the width of each of our rectangles, and this is just our starting interval. So now we have a way to describe the width, and we have a way to describe the height. So let's write this as a summation, because we know that we're going to be adding up all of these rectangles. So we have, starting at the first term, and we're going to do the width, which is b minus a over n, times the height, which is f of a plus I times b minus a over n. So remember, for the first term, I will be 1. For the second term or rectangle, I will be 2. For the 50th term or rectangle, I would be 50. And then, of course, since we are trying to make this as accurate as possible, we're going to find the limit of this summation as n approaches infinity. So this is the formula that we can use to calculate an extremely accurate area under our curve. So here's just a recap of what we've just defined. We're going to be using summation notation to find a way to describe the area of each rectangle. So this is the width of each rectangle. This was that height of each rectangle. And then we're going to take the limit as n approaches 0. So remember, n is really just the number of triangles. So as the number of triangles increases, we are able to reduce that overestimate or underestimate depending on the graph, and we'll get a much more accurate value. Okay, let's see if we can give one of these a try. So here we have the graph f of x equals x squared, and we want to find the area of the curve between x equals 0 and x equals 1. So let's sketch a quick picture here. So we have something like this. Here's x equals 1, and then 0 is at the origin, and they would like us to find this area. So let's start by defining what would be the width of each of our rectangles. So remember, that can be found by doing b minus a over n. So our b value is 1, our a value is 0, so our width is going to be 1 over n. Now let's see if we can define what the height will be. So remember, that's f of a plus I times our width, b minus a over n. So here it's going to be f of a is 0 because that's our starting interval. So plus I times our width. Our width is 1 over n, so it's just I over n. And then I can evaluate this function. If I go and I substitute I over n into our function, I over n squared is just I squared over n squared. So we want to find the sum of 1 over n, our width, times I squared over n squared, which is our height. Now, from here, this is exactly what we've learned yesterday when we learned to find the limit of a summation. So remember, our first thing we're going to look for is any type of constant that we can pull out to the front of our summation. So I noticed that our constant is going to be 1 over n cubed. So I'm going to pull that out front. That's one of our properties of sums. And what I have left is just I squared. So we have a formula for this. So the sum of the first n terms of the series I squared is n times n plus 1 times 2n plus 1 all over 6. And now we're going to multiply this out, so then we can evaluate this as the limit of this as n approaches infinity. So if I multiply out my numerator and then I multiply in the 1 over n cubed, we are left with 2n cubed plus 3n squared plus n over 6n cubed. And once again, we're going to evaluate that limit as n approaches infinity. And since I noticed the degrees in my numerator and denominator are equal, that limit is just going to be that ratio of the coefficient. So it's going to be 1/3. So the area under the curve between those two intervals is 1/3. And that is a very accurate calculation of that area. Okay, let's try one more example together. So here we have a new quadratic function, 3x minus x squared. So let's just do a really quick sketch of what that looks like. So that looks something like this. And the area between the intervals 1 and 2. So here is the area that we will be finding. So in this case, our a value is 1 and our b value is 2. So let's go through that same process. Let's first find a way to describe the width of each of our rectangles. So remember, it's b minus a over n. So 2 minus 1 over n is 1 over n. And then the height of our rectangle is going to be, remember, f of a. So a is 1. So 1 plus I times our width. So plus I over n. So from here, we can evaluate f of 1 plus I over n by substituting it into our function. So it's going to be 3 times 1 plus I over n minus 1 plus I over n squared. So if you multiply that out and combine like terms, we end up with 2 plus I over n minus I squared over n squared. So that's going to be the height of each of our triangle or rectangles. So now let's set up our summation notation. So we have our width, which is 1 over n, times our height, which is all of this. I'm going to evaluate this summation by essentially distributing this value into each of them and finding the sum of each of these terms individually, which is once again one of our properties of summations. So for that first one, I can do 1 over n, which is a constant, times the sum of the term 2, which is also a constant function, plus, now if I distribute this to my second term, I have I over n squared. So my constant value is going to be 1 over n squared, which I can pull out front. And I'm left with the sum of I. And we know a formula to evaluate the first n terms of I. And then for my last term, if I distribute this to my last term, I'm left with negative I squared over n cubed. So I'm going to pull out that negative 1 over n cubed as my constant. And then I'm going to evaluate the rest of that summation, which is just I squared. And once again, we have a formula to evaluate the first n terms of I squared. So let's go back and evaluate this first summation. Remember, for a constant function, you just take your constant and you multiply it by this top number. So we end up with 2n over n. Then I'm going to multiply it by that scalar multiple out front. And then for my second one, the sum of the first n terms of I is n times n plus 1 over 2. And then I'm going to distribute in that 1 over n squared. And then for that last one, the sum of the first n terms of I squared is n times n plus 1 times 2n plus 1 over 6, and then we're going to distribute in this n cubed. So at this point, you're going to have to go through and make a common denominator so we can add them all up. So we could say 12n cubed over 6n cubed plus 3n cubed plus 3n squared over 6n cubed, and then minus, and I'm going to multiply out the numerator of this term, so it becomes 2n cubed plus 3n squared plus n over 6n cubed. And then if I combine those three terms, we're left with 13n cubed minus n over 6n cubed. So now this is the expression where I'm going to evaluate the limit as n approaches infinity. Remember, the main idea behind this is that we want to make the number of rectangles as many as possible, because the more rectangles we have, the more accurate our calculation will be. Now, once again, our degrees in the numerator and denominator are the same, so our limit is the ratio of the coefficients of those terms. So it's 13 over 6. Let me add in units squared. That's the area under that curve between the intervals x equals 1 and x equals 2. All right, so at this point, I'm going to have you pause the video and give this problem a try. I understand if you're still having trouble grasping where the formula for that width and height came from, but at this point, just see if you are able to use the formula, and I think the more you use it and work with it, the more it will start to make sense. All right, let's go ahead and check our work. So first, let's look at the setup before we look at evaluating that summation. So our width is going to be b minus a over n, so it's going to end up being 2 over n. The height, remember, is f of a plus I times our width. So we have f of 1 plus 2i over n, 2 over n times I. So now we can evaluate this by plugging it into our function, which was x squared plus 2. So we have 1 plus 2i over n squared plus 2. If you multiply out that binomial and combine like terms, you're left with this. So here is our summation for the width times the height of all of our rectangles. So we can evaluate all three of these sums separately. So this sum is evaluating here. It's evaluated. Here it's a constant function. This sum, if I distribute this in, our constant is 8 over n squared, and then we have the summation of I. And then if we distribute this in, our constant is 8n cubed, and then we have the summation of I squared. So if you multiply those out and you use the formulas, here's what you get. And from there, you just have to kind of go through the process of multiplying out all of your numerators, creating a common denominator, and then combining like terms. So what you end up with is this expression, which you're going to evaluate the limit as n approaches infinity. And so since the degrees are the same, you take the ratio of the coefficients, and 76 over 6 is 38 over 3 units squared. All right, that is all for today's lesson. Thank you so much for watching.